Greetings to fellow students. We are the last group to present. We are the group 4 from grade 12 STEM Archimedes. Our topic for today is all about motional EMF to be discussed by John Dave Diano, eddy currents and damping to be discussed by me, June Pinlac, and along with sample problems and application to be discussed by Archangel Raphael Abalos. Before we start, let us meet the team with our leader and the following members who greatly contributed to making this output possible. Next is we have the table of contents which comprises of introduction, motional EMF, eddy currents, and magnetic damping, and summary and main points.
We have three objectives in this lesson video. First, we will have to define motional EMF and to calculate the EMF, the force, the magnetic field, and the work due to the motion of an object in a magnetic field. Second, explain the magnitude and direction of an induced eddy current and the effect that this will have on the object it is induced in. And lastly, define the concept of magnetic damping and to describe several of its applications. Let us start. Bago tayo dumako sa kung ano ang EMF, we should know first what does EMF stands for. And according to sciencefacts.net, EMF stands for electromotive force, and it is defined as the energy per unit charge that is generated by a source of electrical energy, such as a battery or a generator. It drives an electric current through a circuit, and it is also known as the voltage, and its unit of measurement is volts, or the capital letter V. In reality, the EMF, or the electromotive force, is not a force, but rather a measure of energy. The source converts one form of energy into electrical energy. For example, a battery. It converts chemical energy into mechanical energy through a generator. We will refer to this image to further visualize the EMF. So first, we have to establish that EMF, or the electromotive force rather, or also known as voltage, is not a force, pero ito ang responsible or ito ang nagkukos kung bakit ang mga charged particles such as electrons move in an electric circuit. It is a measure of the potential difference between 2 points in a circuit, and these charged particles or yung mga charged particles na ito or yung mga electrons na ito move from these 2 points, move from the higher potential point to the lower potential point. In other words, EMF is the energy na nata-transfer from a source of electric energy to an electric circuit. And now, let us go to the definition of motional EMF. Firstly, we have to remember that any change or anumang pagbabago sa magnetic flux ay nag-i-induce ng EMF na nag-o-oppose sa pagbabagong iyon, and this is called as induction. And also, primary cause of induction is through motion. In this section, mag-focus tayo sa isang object or a conductor in motion in a magnetic field that is stationary relative to the Earth, that produces what is called as motional EMF. Motional EMF, the EMF induced in a conducting rod when it comes or when it moves in a region of magnetic field. We can say that motional EMF is a kind of EMF that happens as a result of a conductor moving, specifically a rod, moving in a stationary or hindi gumagalaw or at constant magnetic field. Motional EMF happens when there is a change in EMF due to emotion or due to some motion by a conductor in a magnetic field. But on the other hand naman po, ang induced EMF is nangyayari or created whenever there is a change naman in the magnetic flux through a loop. And this phenomenon ay tinatawag na Faraday's law. We have three factors that affects the motional EMF. 1. The magnetic field. 2. The magnitude or the length of the rod. 3. The magnitude of the velocity or the speed of the rod. Since we are talking about a conductor or a rod moving at a certain type of speed. Here we have a magnetic field, and this magnetic field is constant, and it is going straight out or perpendicular to the surface of this loop. The magnitude of the magnetic field at any point of the surface is labeled as uppercase letter B. And as you can see, here we have is a cylinder that can move to the right. Thus, the right part of the loop is movable. And since this cylinder is moving, we will have the magnitude of its velocity labeled as the lowercase letter v, and the cylinder or the length of the cylinder as uppercase letter L. And since again, we are talking about a cylinder moving to the right across this surface, we will have a change in the area of the surface of this loop. And because of these changes, we will have a change in flux. And this change in flux will induce a voltage in this loop which will cause a current to flow. The formula of electromotive force can actually be obtained through the Faraday's law. Thus, the very first thing that we need to do to obtain the formula of motional EMF is to write down the formula of the Faraday's law, which is EMF is equals to negative N multiplied by the change in magnetic flux over change in time, where negative N is the number of loops, our numerator is the change in magnetic flux, and our denominator is the change in t or the change in time. But in terms of motional EMF, what is our change in magnetic flux going to look like? It will going to look like this. Negative N, we will going to disregard that one, we will just going to focus in the change in magnetic flux over change in time. So, change in magnetic flux over change in time is equals to change in B multiplied by A over change in time, where B is the change in our magnetic field that is perpendicular to the surface multiplied by A, or area of the surface, all over T, or the change in time. But remember that in motional EMF, our magnetic field is constant since our magnetic field is stationary. And since we are talking about an object at motion in a stationary magnetic field, or a rod, specifically a rod moving at in a stationary magnetic field, we will incorporate distance later on, which means that there is a change in area. So instead of a constant B, we will have a rather so instead of a change in B, we will have a change in A instead. So instead of that formula, we will going to have this one. Change in B multiplied by A over change in time is equal to B multiplied by change in area of the surface over change in time. Let's let delta t go on and focus on delta A, or the change in area of the surface. And we have to remember that in order to get or to attain the change in area of the surface, we have to multiply, or kailangan nating i-multiply yung distance taken, or how far will the cylinder go after delta t, or given at a given certain point of time, multiplied by the length of the rod. And now we have to know how to get the distance. So in order naman to get the distance, we have to multiply the magnitude of the velocity, which is given, times the change in time. Thus, the change in area will be the length of the moving rod, or the L, within that magnetic field times the magnitude, or the velocity of the moving rod, over how much time goes by. So, change in B, rather, B multiplied by change in A over change in time is equals to B multiplied by A, or LV times change in T. So, B multiplied by the length of the rod times the velocity times the change in time over change in time. With the current formula, we will going to cancel both change and time. So, we will be left with E, or EMF, is equals to LVB. So in conclusion, our simplified formula, or our motional EMF formula, is equals to L, which is the length of the rod, V, the velocity of the moving rod, and B is the magnitude of the magnetic field. There are numerous applications of motional electromotive force. Any device that provides or gumagamit ng electrical energy can induce electromotive force. Examples of EMF in real-life applications includes electrochemical cells, thermoelectric devices, solar cells or solar panels, electrical generators, transformers, and etc. In electrical generators, or generators in general, these are devices which convert mechanical energy into electrical energy. Ang mga ito ay nag-i-induce ng electromotive force sa pamamagitan ng pagpapaikot ng isang coil sa magnetic field. These generators force electric charges to flow through an external electric circuit to power a house or an appliance or even a whole building. And also, solar cells or solar panels. I believe most of us are familiar with this. So instead of converting mechanical energy, solar panels or solar cells uses solar energy or light energy to be converted into rather electrical energy. With the same use as electrical generators, they also power appliances, houses, or buildings.
Now, we will be discussing about sample problems related to motional EMF from OpenStax chapter 23, numbers 18 to 20. Let's start. So first, letter A. A non-ferrous screwdriver is being used in a 2 Tesla magnetic field. What maximum EMF can be induced along its 12 centimeters length when it moves at 6 meters per second? And for letter B, is it likely that this EMF will have any consequences or even be noticed? So first, our given for letter A is 2 Tesla, 12 centimeters, and 6 meters per second. Now what is being required here is the EMF, or the voltage. And our equation will be EMF is equivalent to the length of an object that is moving at a speed relative to the strength or the magnitude of its magnetic field. The solution will be L multiplied by V multiplied by B. This will result in a 12 times 10 raised to negative 2 meters multiplied by 6 meter per second multiplied by 2 Tesla. This will result in a voltage of 1.44. Therefore, the 1.44 voltage is the maximum EMF that can be induced in the object. Baka napaisip kayo kung paano nagiging voltage ang unit of measurement ng motional EMF. Well, first, ang derived unit of voltage ay voltage is equivalent to kilogram multiplied by square meters over cubic second by amperes, while the magnitude of the magnetic field or Tesla has an SI unit of kilogram over squared second by amperes. Kapag in-apply with the motional EMF formula to nagka-come to terms siya with the derived unit ng voltage. Thus, ang unit ng measurement niya ay voltage. And for letter B, no. It is not likely that the EMF will have any consequences or even be noticed. Dahil ang 1.44 voltage na nakuha natin is similar to AA battery, which has a small amount of voltage. Therefore, our answer is that the maximum EMF can be produced in the object is 1.44 voltage. And no, since it is not likely that the EMF will have any consequences or even be noticed due to the small amount of voltage. So for our sample problem number 2, at what speed must the sliding rod in figure number 1 move to produce an EMF of 1 volt in a 1.50 Tesla field, given the rod's length is 30 centimeters. So una, ang given natin is 1 volt, 1.50 Tesla, 30 centimeters, which is the length ng rod. Based from the problem pa lang, ang ano natin is speed. Bali, using the motional EMF and deriving it, mahanap natin ang value ng speed. So, para mahanap natin ang speed, we must divide both sides by L and B in the equation. So, which leave us in cancelling both L and B on the right side. Kaya ang matitira na lang sa equation natin is velocity is equivalent to EMF divided by the length of the rod times the magnitude of the magnetic field. So this will be our solution, which is the 1 volt over 30 multiplied by 10 raised to negative 2 meter multiplied by 1.50 Tesla. So our velocity will be 2.22 meters per second. Yun ang necessary na speed ng sliding rod. So for our sample number 3, we have a 12 centimeter long rod in figure number 1, which moves at 4 meters per second. What is the strength of the magnetic field if a 95 voltage EMF is induced? So first, our given is the length, which is 12 centimeters, followed by a velocity of a 4 meters per second. We also have a 95 voltage, which is the EMF. So in this problem, halos parehas sa problem number 2. However, in this case, ang hinahanap natin ay ang B or yung magnitude ng magnetic field. So again, using the motional EMF at pagde-derive nito, mahanap natin ang value ng B in deriving the formula by dividing both sides by the length and the velocity. So bali ang mangyayari dyan is i-cancel natin ang LV on the right side na matitira sa atin, which is yung letter B is equivalent to EMF divided by the length times velocity as our equation to be used in this problem. So ang magiging solution natin dyan is ang 95 voltage over 12 times 10 raised to negative 2 meters multiplied by 4 meters per second. So ang makukuha natin dyang magnitude ng magnetic field ay 198 Tesla. Yun yung necessary na kailangan natin para ma-produce yun.
Now, para sa ating next topic, it's all about eddy current and magnetic damping. So let's now begin. Gaya ng tinalakay sa motional EMF, ang motional EMF ay induced kapag ang conductor ay kumikilos sa magnetic field or when a magnetic field moves relative to a conductor. Kung ang motional EMF ay maaaring magdulot ng current loop sa conductor, tinutukoy ang current na iyon bilang isang eddy current. Eddy currents can produce significant drag called magnetic damping on the motion involved. To further understand, here are the definitions. What is eddy currents according to McGrath 2015? Ito ay currents na dumadaloy sa conductors na may direction na circular motion sa mismong conductor na dinadaanan nito. Maaari silang malikha kapag ang isang conductor ay gumagalaw sa isang magnetic field o kapag ang magnetic field na nakapalibot sa isang nakatigil na conductor. Para mas maintindihan ng eddy current, here's a demonstration video from respected link. In the video, merong silver bar which is the neodymium magnet. It is very large, industrial strength magnet na made of rare earth metal at gawa sa iron, boron, and nickel. Meron itong two sides, north side at south side. Habang ang bronze naman ay piece of pure copper. Ang magnet na i-induce sa copper ay eddy current na bumubuo ng small pools of swirling electrons upang pigilan ng paggalaw ng magnetic field na i-induce ng neodymium magnet sa copper. Pinipigilan nito ang magnet mula sa paghulog tulad ng isang normal na bagay tulad ng piece of wood. Nagkakaroon ng cushions to itself at as you can see, pwede mo itong spin, i-drop at mag-i-induce ng torque into the copper from magnet itself. Kaya't nang hindi hinahawakan ay naigagalaw ang copper. Next, let's head to damping. A damping force is generated when this eddy current and magnetic field interact with each other. This is called magnetic damping. Ang damping ay gumaganap ng isang mahalagang papel sa pagkontrol sa motion ng isang bagay. According to BYUGAS, damping an opposition over the motion of an object, the damping tends to reduce the speed of moving object. In our lesson that relates to motional EMF and eddy currents, ang damping technique na ating ipofocus ay magnetic damping. Again, BYUGAS says that magnetic damping uses magnetically induced current to control, regulate, slow down the motion of the object without any actual physical contact with the moving object. While Wikipedia says that it is also a form of damping that occurs when a magnetic field, example magnet, travels some distance through or past an electrical conductor or vice versa. Ito yung method ng removing of energy para makontrol yung vibration, motion tulad na lamang ng ingay or ugong, mechanical oscillation, and alternating electric current. Nangyayari ito kapag walang pagdikit na nagpapaliit ng paggalaw at nag-spread ng energy. Ito ay isang form ng damping na nangyayari kapag ang magnetic field or for example magnet nagta-travels into the distance, papasok or palabas sa electrical conductors or vice versa. For the example, a common physics demonstration device for exploring eddy currents and magnetic damping is given. To further understand, a video demonstration from CG Physics will be shown. Bakit nga ba tumigil sa paggalaw yung pendulum? Ang aluminum plate na gumagalaw in a pendulum motion ay nag-enter sa magnetic field. Sa pagpasok nito, ang magnetic flux na nag-handle dito ay nagsisimulang tumaas at bilang resulta nito ay mayroong EMF induced na tinatawag na motional EMF. Ang EMF na ito ay nagsisimula ng mag-produce ng eddy currents at kapag ito ay nag-exit at sa pag-exit nito, ang magnetic flux naman ay bumababa na nagpapabagal dito. Yung na-induce na current sumusubok na tumaas at magnetic flux bilang resulta na nag-attract ito sa magnet or get attracted towards the magnet. Ito ay babagal at kalaunan ay titigil.
Sample applications of eddy current and magnetic damping. So ngayon naman, we will provide more applications of eddy currents at magnetic damping from OpenStack College Physics Chapter 23.4, Eddy Currents and Magnetic Damping. So for number 1, sensitive laboratory balances. To have maximum sensitivity and accuracy, the balance must be as friction-free as possible. Pero kung ito ay walang friction, then mag-oscillate ito ng napakatagal. Kaya magnetic damping is a simple and ideal solution. With magnetic damping, drag is proportional to speed and becomes zero at zero velocity. Thus, the oscillations are quickly damped, after which the damping force disappears, allowing the balance to be very sensitive. Magnetic damping of this sensitive balance slow its oscillations. Since ang Faraday's law of induction ay nagbibigay ng greatest effect para sa rapid change, ang damping ay greatest for large oscillations at napupunta sa zero habang humihinto ang motion. Use of magnets to separate metals from other materials in recycling centers. Since ang eddy currents at magnetic damping ay nag-occur lang in conductors, recycling centers can use magnets to separate metals from other materials. For example, trash is dumped in batches down a ramp, beneath which lies a powerful magnet. Conductors in the trash are slowed by the magnetic damping while non-metals in the trash carry on. Separating from the metals, this works for all metals, not just ferromagnetic ones. A magnet can separate out the ferromagnetic materials alone by acting on stationary trash. Maaring ihiwalay ang mga metal sa ibang basura sa pamamagitan ng magnetic drag. Ang mga eddy current at magnetic drag are created in the metals sent down this ramp ng malakas na magnet sa ilalim nito, habang ang mga hindi metal ay magpapatuloy lamang. So for number 3, we have metal detectors. Portable metal detectors consist of primary coil carrying an alternating current and a secondary coil in which a current is induced. An eddy current will be induced in a piece of metal close to the detector, which will cause a change in the induced current within the secondary coil, leading to some sort of signal like a shrill noise. So eddy current produces a magnetic field that induces currents to any metal objects that are nearby. The metal objects can easily locate or detected since the current that is induced can generate its own magnetic field. Yun ang dahilan kung bakit ang mga eddy current ay kadalasang ginagamit sa mga metal detector. Dahil sa kanilang currency that can allow you to locate ang mga nearby na bagay na metal na nakakatulong sa iyong mapapansin kung ang bagay na iyon ay dangerous ba o hindi.
To sum up everything, EMF is the energy per unit charge that is generated by a source of electrical energy. The term motional EMF refers to the creation of an electric field that results from the movement of a conductor within a magnetic field. We have three factors that affects the motional EMF. 1. Magnetic field. 2. The magnitude of the length of the rod or the conductor. 3. The velocity or the speed of the moving rod. This motion alters the magnetic flux which induces a voltage across the conductor, producing motional EMF. Motional EMF is beneficial for various functions, such as generators, which provides power or electricity to some of our households. On the other hand, eddy currents caused by the motion of a magnetic field creates circular currents in the conductor which impede the flow of current and result in energy loss as heat. Eddy currents arise in a conductor due to a magnetic field or motion, resulting in energy loss and heat generation. It has practical applications. It includes metal detection, induction heating, and magnetic levitation. Eddy currents can produce significant drag, which is called magnetic damping. Magnetic damping also affects conductor motion, as the magnetic field opposes the motion and slows it down. This employs induced electromagnetic current to manage, direct, or restrain the movement of the entity without the need for physical interaction with the in-motion entity. As the magnet and conductor moves closer, the damping force grows bigger. The electromagnetic damping force is directly related to the eddy current that is induced, the strength of the magnetic field, and how quickly the object moves. Thus, the faster the object moves, the stronger the damping force will be, while slower object movement will cause less damping, result in a gradual stopping of the object. That is all for our report on behalf of the group. We thank you for watching and listening.